Hello, welcome to a speedrun tutorial of how to use NASA CEARun. If you hear random people screaming at random times, don't be alarmed. It's my roommates are doing something outside, I don't know what, but here we go. So this is the page that we land at when we go to NASA CEARun. There's different problems that you can select. Today we're going to be working with the rocket one. Feel free to explore the other ones if you like. So we first land in this page of pressures, and there's two ways you can input pressure. One is you have a range of chamber pressure that you want to change and see what the values are, and one is if you just need a single case. So if you need multiple cases, you use your left side, and if you need just one case, you use your right. So in terms of how to select in terms of how to use multiple cases, let's say I want to run a chamber pressure of 1 to 10 bars with an interval of 1. Then I just put 1, 10, 1. And now whatever I run for the rest of the problem, they will give me conditions that chamber pressure is equal to 1, 2, 3, 4, 5, so forth. And on the right is if you just need a single chamber pressure. So let's say 30 bars is what we're going to be working with. And then here you just make sure your units are selected correctly and you click accept input. Then you land on the field page. Here you have some common field if you want to use them, but of course we're dealing with our paraffin wax, which you will not be able to find here. In that case, we have to use the periodic table. So CA is a pretty big database. CA stands for chemical equilibrium analysis, and there's a lot of compounds that you can choose from. Today we're working with paraffin wax, and we know that paraffin wax is a hydrocarbon chain, so we just select C or H. And if you're working with some other elements or compounds, you just select whatever element is contained within that compound. So I click C and H, I select. We are and then we get all sorts of compounds with C and H. Paraffin has its own unique option, so you just click paraffin and click accept. And today, if you choose more than one field, then you're going to be led to this page. I mean, you'll be led to this page no matter what, but if you had more than one field, there would be like another column here, and then it would be like, let's say like methane, and then you would enter your different percentages so CA can do its math for the mixture. Click accept input. Here you don't really need to insert the insert properties at all unless you're working with something unusual, but otherwise CA already has its default values for different compounds and you can just use them as is. So accept. Now we land at the oxidizers page where we're working with nitrous oxide. We don't see, and then we see nitrous oxide here, so we can just go ahead and click N2O. Similarly, if you do not find the oxides that you want, CA most likely has it. You would just use periodic table and find it. Now you hit next. We are at the OF ratio page, and this is actually pretty important to know, so pay attention. So OF ratio, a lot of times, or a lot of problems that we're solving with, remember how specific there are different ISP values at different OF ratios, and at one fixed OF ratio you're going to get the greatest specific impulse, which is typically where you get the largest thrust. Similarly, largest or around that area characteristic velocity. But at first we're dealing with a fuel propellant combination that we do not know what that optimal OF ratio is. NASA CA is where we go to. So today let's say if I didn't know what the optimal OF ratio for paraffin N2O is, then I would just start roughly. Okay, so 1 low value, 1 high value 10. At first I just want initial guess. I don't really care how precise it is, but so let's go with 0.5. So it's gonna go 1, 1.5, 2, 2.5, da. And then similarly, if you just want one value, you can fill in the box here. But today, let's assume that we don't know what the optimal OF ratio is. We click accept input and continue. Alright, this is pretty important. You're always going to get these three boxes, but you don't care about your subsonic error ratios or your supersonic error ratios. These are just different ways you can define your exit condition. We'll go the easiest way, which is always assuming that our engine is going to be operating at sea level. Obviously, you might optimize it differently depending on your trajectory of your engine. Maybe you want it to be more efficient at higher stages of flight, higher altitude, but today, let's say we're just working with sea level. Now, all you have to do is input your chamber divided by exit pressure ratio. So I know that my chamber pressure is 30 bars, right? And I know that I wanted to exit at ambient pressure, which is around, I think, 1.1. So 1 ATM is equal to 1.14 bar or something. So in this case, my ratio would probably be like 29.456, or I don't know, like should be around 29 something, and I got that by dividing 30 bar by the atmospheric pressure in bar. So that's why I have 29.564. And beware, if you do not put anything here, you will not get anything at throat or nozzle exit because it's unable to define a nozzle for you, and therefore you won't be able to get things like expansion ratio that you need for the engine. So now click accept input and you're led to this page. So over here there are different things that you are looking at. Don't worry, all you have to select is equilibrium. I won't go into details, that might take some time, but just use equilibrium and let's first run it and see what you get. So you're led to this page and then you get all sorts of values here. So remember how we were iterating through different OF ratios? Here it tells you what conditions you're iterating through. So over here I see that, okay, this is my pressure, 30 bar, this is my nozzle conditions, and these are the OF ratios I'm iterating through. I scroll down and I can find our first case. In this case, we have OF ratio is equal to 1, and that's the only thing different across our trials. So here you can get everything that's related when your OF ratio is equal to 1. So specific things you have to look for. This tells you the pressure at different point of your nozzle. This tells you your temperatures in Kelvin. This tells you some other things which you don't really have to know unless you're doing some chemical analysis. And then here's your Mach number. Sorry, no, this is your Mach number. And then here you have your specific heat. And if you're using the isentropic equations, and correct me if I'm wrong, but you should always use your chamber specific heat ratios because of how the equation is set up. But here you get stuff like expansion ratio, which you need to calculate your nozzle exit area. And then you have your C star, thrust coefficient CF, and then you have your specific impulse in vacuum, and you have your specific impulse under normal conditions. And just remember that because ISP is in seconds, you have to divide these two sets of values by 9.81 to actually get the values that you see in literature. And here are some of the mass fractions, which is most typically used in CFD calculations, so you don't really have to mind them. But what we see right now is kind of results broken down into different OF ratios. But what if I wanted to have it tabulated nicely somewhere, or have one way where we can separate the data? Well, in that case, click final. We go back to where we were. We put tabular results for insertion into a spreadsheet, and then we click long print out output tables, and then submit perform C analysis, and it's gonna take you here. Here you just basically call for the things that you want. So for example, I want my cross section area or my throat area. I put AEAT. If I actually no, let's just start simple. You can call whatever variables you want, but let's say today I just want my gamma. Right? And I also just want my, where's my ISP? I just want my ISP. Okay, let's say I just need these two things. Then I click submit. Did I type gamma wrong? Yes, I did. It's gam. Submit. Here it's gonna take you here, but so it does tabulate things. Here they don't tabulate things for you. You're gonna see tables similar to before, but on the right top here you're gonna see an option called tabulation, and now it tells you your specific impulse and gamma at the intervals that you have chosen for your OF ratio. And I believe so you might see, like, so we know we iterate through, I think 20. Well, basically you see different values here, and the first value here tells you the chamber, second value tells you your so remember, because an engine is divided into chamber, throat, and exit, so this is what the three values correspond to. So this is your first OF ratio, and then this is your second whatever OF ratio in that interval. This is your third, this is your fourth, and so on. So you can process that, and it should take you and you should have everything that you need.